Welcome to the Explainer. Look, if you're out there working with designing or specifying heating, ventilation, air conditioning, and refrigeration systems, HVACR, right? You already know that the environment is literally your equipment's biggest enemy. Today, we're going to translate the absolute alphabet soup of protection classes. We're comprehensively breaking down IP ratings, NEMA standards, and atmospheric corrosivity. So, let's dive right in and figure out how to properly shield our gear and stop catastrophic failures before they even start. Here's our quick roadmap. We'll start with why HVACR systems actually fail, decode those ingress protection and NEMA enclosure standards, explore atmospheric corrosivity categories, and then finally put it all together in a really high-stakes case study protecting air handling units. All right, moving right into Section 1, why HVACR systems fail. Because before we talk about the shields, we really need to understand the invisible weapons being used against us. Let me just throw this question out there. Why do industrial cooling motors actually fail? Seriously, think about it. Because field experience across HVAC and process cooling systems tells us something super important. Most of these failures, they aren't random. It's not just bad luck. It almost always boils down to a few recurring specification issues. And man, you can really see what happens when those specs fall short. Just look at the visceral rust and corrosion on that motor housing. There's no way around it. The data points to 4 main root causes here. First up, inadequate IP protection. When motors are exposed to water spray without proper sealing, moisture gets right in, and boom, internal corrosion. Second is a low insulation class. Cooling tower motors are running under continuous load, and your standard Class B insulation, it usually just doesn't have the thermal margin compared to Class F or H. Number 3 is undersizing, which jacks up thermal stress and completely slashes the service life. And finally, condensation hitting the bearings. See, temperature swings cause internal moisture cycles, what we call thermal breathing, and that just tears through lubrication and accelerates bearing wear like crazy. Okay, so how do we actually stop that moisture ingress and thermal breathing? Well, let's get into our first line of defense with Section 2, decoding IP rating standards. So, IP. It stands for Ingress Protection. It's a very specific, standardized method set by the International Electrotechnical Commission under the standard ISC 1659. In plain English, it tells us exactly how well an electrical enclosure can withstand dust particles, solid objects basically, and water. It's a totally crucial metric. Without it, we'd just be guessing, calling things splash-proof, which, let's be honest, is a fast track to broken equipment or worse, someone getting hurt. The trick is really just understanding how to read this 2-digit code. Think of it like a puzzle. That first digit, that's your protection against solid objects. It scales from 0, meaning 0 protection at all the way up to 6, which is completely dust tight. So it blocks everything from, someone's hands or fingers down to microscopic dust. Then you've got the second digit, which is all about liquids. That one ranges from 0 to 8, with 8 meaning you can basically dunk the thing continuously in water and it'll be fine. Let's walk up this ladder of protection so you can see what these industry standards look like in the real world. Step 1, IP21. This blocks solid objects over 12 millimeters, so fingers, and vertically falling condensation. It's your basic, everyday standard for clean, indoor plant rooms. Step 2 bumps us up to IP55. Now we're blocking limited dust ingress and low-pressure water jets from absolutely any direction. You definitely want this as your baseline for outdoor cooling towers or variable speed drives sitting out in the elements. And then step 3, the absolute extreme, IP69K. This means the enclosure is completely sealed tight against dust and can take a massive beating from intense, high-pressure, high-temperature washdowns. Real heavy-duty stuff. Now, while IP is an international standard, North America actually plays by its own set of rules. So let's jump to Section 3, understanding NEMA enclosure ratings. Okay, so this is where it gets really interesting. The NEMA rating system looks a lot like the IEC's IP codes, but they are absolutely not exact clones. Remember, IP codes only care about blocking solids and liquids. That's it. But NEMA? NEMA goes way further. It mandates things like gasket aging, specific construction practices, and, this is the big one, corrosion resistance. And because NEMA packs in all those extra durability requirements, you literally cannot just take a NEMA rating and perfectly map it backward to an IP code. It doesn't work that way. It's strictly a one-way street here. You can take an IP code and translate it into its minimum required NEMA standard to hit those criteria. For example, an IP20 maps over to a NEMA 1 enclosure, perfect for indoors where you aren't worried about water. IP54, that maps to NEMA 3, which keeps out falling rain and sleet. And IP65 maps up to a NEMA 4 or 4X, bringing in special gaskets for washdown situations. Then IP67 takes you to NEMA 6 for temporary immersion, and IP68 brings us all the way to NEMA 6P for prolonged underwater submersion. But remember, you always have to double-check these minimums against what your specific application actually needs. All right, so we've talked about the boxes, the enclosures shielding our motos and drives. But what about the actual air wrapped around those boxes? Let's zoom out a bit in Section 4, Atmospheric Corrosivity Categories Explained. I want you to just think about this number for a second, 2,500. Any idea what that is? That is literally the number of hours every single year that massive parts of Europe spend sitting at over 80% relative humidity with temperatures above freezing. That's enough time to cause some serious damage. It perfectly highlights the super important concept called the time of wetness. Because look, a corrosive environment isn't just about chemical pollutants. It's massively accelerated by humidity and that constant, severe risk of condensation. To make sense of all this, the ISO 9223 standard breaks atmospheric corrosivity down into specific categories. Let's map them out really quick. We start at C1, which is very low corrosivity. We're talking heated indoor spaces, offices, schools, basically zero pollution. Skip ahead to C4, and now we're hitting high corrosivity. This is your indoor swimming pools or chemical plants. C5 is very high. This is heavy industrial areas, coastal zones getting blasted with chlorides, or anywhere dealing with super high condensation frequencies. And finally, CX, extreme. This is the wild stuff. Offshore rigs taking constant salt spray, places where condensation is basically permanent. And listen, whatever category you're in, it 100% dictates the materials you absolutely have to use for your equipment. So, how does all this theory actually play out in the field? Let's bring it all together in Section 5, Protecting Air Handling Units, with a real-world case study. Picture this, the extract air coming out of an indoor swimming pool. It is, without a doubt, the absolute perfect storm for corrosion. Your air handling unit is sucking in air that's sitting somewhere between 28 and 32 degrees Celsius, loaded with 50 to 60% relative humidity. But here is the real kicker. That air is packed with chloramines, specifically this incredibly aggressive nitrogen trichloride. This hot, wet, chemical-heavy air means the exhaust side of the unit is just incredibly vulnerable. Throw a standard metal casing in there? Yeah, no way. It simply isn't going to survive. Since a swimming pool is officially a C4 corrosivity environment, you have to match your materials to that exact threat level. To actually guarantee that 15 to 20-year lifespan you expect from a heavy-duty air handling unit, you absolutely need to use a high-durability paint system on any steel or aluminum casing. You've got to specify a system built for C4 right from the jump. Because if you don't, both the internal components and the casing itself are going to degrade incredibly fast, leading straight back to those catastrophic failures we talked about at the very beginning of the explainer. Which brings us right to our final takeaway for today. The environment dictates the machine. Are your facility's vulnerabilities adequately shielded? Think about it. Whether it's slapping an IP55 drive in a dusty plant room, picking a NEMA 4X enclosure for crazy washdowns, or demanding high durability coatings for a C4 swimming pool, understanding this entire alphabet soup is really the only way you can guarantee absolute reliability. It's how you stop internal corrosion and motor failure in its tracks. So take a really hard look at your own equipment specs. Are you truly protected? Thanks so much for joining me on this explainer, and keep learning.